In this video, we're going to be talking about a group of functions called the hyperbolic functions. These functions are built out of the exponential function that we saw in the previous videos. Okay, so the idea goes like this. Using the exponential e to the power x, remember e here is just an irrational number, 2.718 something something something, just a number, and we can use that number to create this function e to the power x, where we just take a number x, raise e to that power, of course that defines a function. So using e to the x, we create the hyperbolic functions. And they look like this. So there are three of them that I'm going to introduce for the moment, and the names will look a bit familiar to you from trigonometry. We'll see why in a minute. Right, so the first one is called, well, it's written like this, sine h. Now people often read this as shine. Some people call it sinh, or just sine h. Some people will call it hyperbolic sine. So sine h of x, what is this? Well, it's defined to be a half of e to the x minus e to the minus x. So not hard to calculate. Of course, if you think of a number x, you can work out e to the x nice and easily. You can work out e to the minus x nice and easily. Take one from the other, divide by 2, and that gives you the value of sine h. So that's the first one. Partnered with this, we also have cos h, or cosh, as it's sometimes called, or hyperbolic cos. And that's similar. It's a half of e to the x plus e to the minus x. So if you want to know what cos h of x is, just work out e to the x, work out e to the minus x, add them together, divide by 2. And the third one I'm going to talk about is tan h, also called tanch or than or all sorts. Hyperbolic tan or tan h are probably the safest ones to use for naming it. And this is just sine h of x divided by cos h of x. Okay, so three functions here. They look familiar from trigonometry. I mean, you have sine, cos and tan, where tan is sine over cos. That's all the same, except we've got these added h's as well. And it's all defined in terms of this exponential function e to the x. Okay, so these things are, we'll find, related to the trigonometric functions, even though they don't look it at the moment. I mean, it doesn't look like there's anything to do with trigonometry going here. It's all written in terms of exponentials. But in fact, later in the course, when we get to complex numbers, you'll see that there is a subtle relationship between these and the trigonometric functions. Or indeed, look it up in any textbook you like on this subject. Right, I think we should look at the graphs of these three things. And in fact, the graphs don't look anything like the trigonometric graphs, really. The first one is sine x. Let's draw a set of axes. So here's x, here's y. And what sine x does is it certainly crosses at 0. I mean, if you remember the formula, sine x is a half e to the x minus e to the minus x. Now if you put x equals 0, then you get e to the 0 minus e to the 0, so that will give 0. So it certainly goes through the origin. Now as x gets large, this e to the x term will get really big, but e to the minus x, you'll get things like e to the minus 1,000, e to the minus 10,000, stuff like that. That's going to get really small, because e to the minus 10,000 is 1 over e to the power 10,000. e to the power 10,000 is huge, so 1 over that will be tiny. So really, it just starts looking a bit like e to the x divided by 2, which as we know, will just get really big really quickly. So off in this direction, it starts going up exponentially fast. And a similar thing happens in the other direction. If we go in the negative x direction, it goes off to infinity really quickly, like so. So this is the graph of y equals sine x. And you'll notice that sine here is an odd function. If you like, it's got rotational symmetry through 180 degrees about the origin. Or if you want to do it algebraically, put in minus x instead of x and you'll see that sine of minus x is minus sine of x. Okay, so that's sine. What about cosh? Well, cosh, or cos h of x, that is a half of e to the x plus e to the minus x. Now certainly when x is 0 this time we don't get 0, we'll get e to the 0 plus e to the 0. Well, that's just 1 plus 1, which gives 2. When we divide by 2, we'll get 1. So certainly this graph crosses the axis, crosses the y-axis at y equals 1. Now in fact what it does each side is, over in this direction, as x gets big, it behaves pretty much like e to the power x divided by 2, because this term gets really small, so it goes off, shooting up to infinity. And in the other direction, e to the minus x will get really big, but still positive. So if you put in x equals minus 10,000, then this will be e to the minus 10,000, which is e to the plus 10,000. That's really big, so it's going to, and this term will get tiny, of course. So what it's going to do is the same thing the other side. So this looks a bit like a parabola as I've drawn it, a bit like y equals x squared shifted up, but in fact it grows much quicker in either direction. It goes up exponentially fast. So this is what y equals cosh x, or cos h of x, looks like. Okay, now in fact there's something interesting to say about y equals cos h of x, and that's this shape does have a name in the same way that y equals x squared is called a parabola. This shape is called a catenary, which I think is spelt like that. Now, I'm not an expert on these things, but I think that comes from the Latin. It's to do with the shape a chain makes if you hold it by both ends and let it hang. A chain, or even a piece of string. If you take a piece of string, hold it at two ends, the shape that it hangs in isn't a parabola. It looks a bit like a parabola. It's in fact the same as cosh x. It's called a catenary. Okay, so those are sine and cosh. What does tan h look like? Well, before we draw it, let's just observe a few things. Tan h is sine h divided by cos h. Now, at x equals 0, sine h is 0, cos h is 1, so 0 divided by 1 will give 0, so tan h goes through the origin. The other thing to say is as x gets large, this term becomes irrelevant in cos h of x, this term becomes irrelevant in sine h of x, so really they're almost equal. This one's going to be slightly smaller than this one, but they're almost the same, so sine h divided by cos h will almost be 1, just slightly smaller. And as you go to minus infinity, a similar thing happens. This one's positive and this one's negative, but they're almost the same in magnitude, and in fact sine h divided by cos h is just slightly bigger than minus 1. So let's draw the graph. It's not hard given what we've just discussed. So here is a nice set of axes, x going this way, y up here. Everything happens between 1 and minus 1, so we'll draw dotted lines across like that. And the graph, in fact, fills in asymptotically approaching minus 1, coming through at 0, and then going off like this. So this is y equals tan h of x. Right. Okay, so those are the three basic hyperbolic functions. In fact, you can use those to define some other ones as well. I mean, in the same way that when you have sine, cos and tan, you can do 1 over cos, which is called sec, and 1 over sine, which is called cosec. All those kind of things. Do this exactly the same thing with these hyperbolic functions, as long as you put h's after each of their names.